Okay, so here's our second segment of servicing the 66B. We started the first one with just kind of an overview of the system. One thing that I wanted to add to that I should have talked about was on the RF converter here. In this assembly, all the RF is down converted to the final IF of 21.4 from all the bands. So there's the band 0. It goes from essentially DC to 2.5 gigahertz. It has its own converter, and it is down converted to 21.4. And then the bands from 2 to 22 gigahertz are also down converted to 21.4. The 21.4 is passed out of this chassis into the display chassis where the resolution bandwidths reside. So this is where all the RF signal processing really happens right in this subassembly here. Everything else is really devoted to power supply and synthesis for the YIG oscillator first LO subassembly here. Okay. So one of the things that I said I would talk about in this one is some common problems with the YIG system. In fact, there's going to be a number of videos just about the YIG system in particular. But I did kind of make an error in saying maybe the most common problem. Actually, maybe the most common problem is here in the RF converter, and that is with the attenuator failure. The attenuator is in here is a 70 dB, 10 dB per step attenuator, and that will often fail, and that can be traced to little tiny O-rings that are used to push the plungers that control each attenuator setting. So if you have a problem with that, there's actually some pretty good information on the web about how to service these attenuators, all the HP line there, and replacing those, and usually that's all that's wrong. So that's probably the most common RF problem that happens with this instrument is the attenuator. And that's inside here. You have to remove this assembly to service that. And that's done by taking out a couple of screws on the side. On the bottom, you have to remove both covers, take the front cover off, and then eventually this whole subassembly slides out, which I'll show you right here. Give me a minute. Here's a complete subassembly as it comes out of the instrument. The cards are loose in this one. I can't turn it over too much. So there you can see the bottom. There's two ribbon cables. So this is the subassembly that produces the 21.4 IF. And in here is all the mixers, the YIG tune mixer, the first converter, the second converter, the converter down to 21.4, a multiplier from 100 megahertz up to 300 megahertz, and also a phase lock loop to produce 3.3 gigahertz for the 0 to 25, 2.5 gigahertz band. That's the RF converter assembly. We'll talk more about this later. So going on to the YIG, in here is one of the culprits of the YIG failure. And if you get a YIG unlock message, often it can be traced to the A20 card, which is right here, the A20 card. And in particular, there's a capacitor. This one right here is C7 on the A20 card. This is the original card, and that's the original capacitor, and it was essentially an undersized component from the factory. I believe it's rated at 75 volts, and it's very small at 10 microfarads, and this usually fails in the open, and when it does that, the YIG won't lock. That's not the only thing that can cause the YIG to unlock, but it's one of the most common. And so this is one of the parts that we replace, whether it's bad or not. We take it out and replace it with a modern component, and it's always bigger for that rating. In fact, we usually go up on the voltage, and so that we get rid of that. So that's one of the most common failures that can cause the YIG to not lock. Another failure, or not really a failure, it's an adjustment issue. Sometimes the yigs age or somebody's done something perhaps and there's an adjustment issue. The two most crucial adjustments are on this same card, A20. And these adjustments are done by these two potentiometers right here. This one here is for the 6.15 gigahertz adjustment, and this one is for the 2.3 gigahertz adjustment. We're not going to go through the adjustment procedure today, or in this video, but these two pots, if they are not set correctly, the yig will not lock. And the reason is simple. Well, maybe that's a bad thing to say. It can't find a lock spot. Those two pots essentially set up the yig oscillator to be close to the correct frequency for the M&N and the phase lock loop system produce the correct frequencies and for that yig position of frequency to create a lock mechanism or capability. If the yig is too far off, the loop cannot pull the yig into lock. And so the loop will go open and you'll get the unlock signal. So without a system essentially to get the yig close to where it has to be in frequency, the yig system cannot lock. And the way they do that in this instrument is essentially sum a voltage onto the yig, and that voltage has to be pretty close to where the yig's got to be, and then the lock adds on to that and creates the final lock. So it's really a kind of a two-step process. There's an analog voltage that has to be close to push the yig close to the lock frequency, and then the M&N and the phase lock loop 1, 2, and 3 can take over and cause the yig to lock. So if this is out of adjustment, the yig won't lock. So there's an adjustment procedure to do this. It's not very complicated. It roughly, a few keystrokes and a few, you put a jumper here between this card and this card, A20 and A19. You remove a cable on the yig oscillator assembly, and you can start the adjustment procedure. The adjustment procedure is tedious because each pot interacts with the other one. So when you set the frequency to 2.3, you got to go back and check 6.15 gigahertz, and then you go back to check 2.3 gigahertz, etc. Again, the details of that we can cover at another time, but that's how you do it. I prefer to use a spectrum analyzer. They suggest a frequency counter in the test and adjustments, but with a spectrum analyzer you get to do something else. You get to look at the open loop performance of the yig oscillator, and sometimes that's what's causing other problems, and sometimes it might cause it to not lock. It might be so noisy it can't lock, and you kind of have to know that the yig's got to be clean enough to lock. If it's got some noise issue, it's malfunctioning somewhere else, it may not lock because of noise. You can find out the open loop performance of your yig by just operating the instrument. I'm not going to do that right now. I'll show you that later. And that's fairly easy to do. And you can actually see how clean your open loop yig really is. That is to say, using the instrument by itself, no instrumentation outside of it, just set it up and actually observe the 100 megahertz cal signal on the instrument. And look at that, and you can tell a great deal about the quality of the yig in the open loop configuration. That is, for spans greater than 5 megahertz, as I discussed earlier. When the span is greater than 5 megahertz, you only lock on the very first point of the sweep. So it's possible to see the open loop performance of the yig. So this is one of the things that causes the yig to unlock. Another thing that can cause that is these pots are not adjusted correctly. Another thing that can cause the yig to unlock is bad connections between A20 and A19 to the motherboard. As these systems sit, often a little bit of contamination or something on the PC edge connector, and it'll cause enough noise or a bad connection and it won't lock. So the very first thing to do is take these two cards. In fact, probably take these cards out here and the scan generator card and reseat them and clean the connections with appropriate cleaners and reseat them and see if the lock issue goes away. We also have seen the lock indicator falsely triggered. That can occur because if you trace the logic as it comes, the lock detect is generated in here, and it has to come out of this subassembly and go to the interface card. And in that process, if there is a break in the path, it will float high and it will be a false YIG unlock signal. So sometimes you got to make sure that you're not getting a false YIG unlock. And that's easily done because you can read the voltage when it's locked, or supposed to be locked. If you put the span underneath 5 megahertz, it should be locked all the time, and then set it to 0 span, 0 hertz. You'll just be sitting there at a certain frequency. And you can just look at the tuning voltage, and if it's not within the specifications in terms of when it's locked, which they tell you in the adjustments, then you know it's not locked. So that way you can determine whether or not the lock-unlock indicator is being truthful, is to actually read the tuning voltage. Okay, so I think we've covered most of these issues with A20 and A19. Also the assembly here, I've talked about that. And I think that's it for this segment right now. We're going to go on from here onto other issues. But a lot of what we've covered right now will address many of the YIG unlock symptoms. If you have, in conjunction with the YIG unlock, a phase lock loop 1, 2, or 3 unlock, then that will be maybe the primary cause of the YIG unlock. In other words, if the M&N, which is a phase lock loop, the phase lock loop 1, 2, or 3, if any of those loops open up, they will create a phase lock loop or M&N unlock signal that'll be displayed on the CRT, and those will also cause the YIG to not lock. So a YIG unlock signal by itself is probably the best scenario you could hope for, because it's mostly the most likely simplest problems. If the YIG unlock is accompanied with a phase lock loop unlock, that's a much more serious problem. And so you're going to have to figure out what's going on with that phase lock loop. And in that regards, most likely it's not the M&N. This is a very robust system, and it tends to not be problematic. The problems typically live in the phase lock loop 1, 2, and 3, and in particular, the phase lock loop 2 subsystem. And I'm just going to go off the script here a little bit and say that the phase lock loop 2 system is the primary system of interest. The reason is that you can set up the instrument so that it is the only one of the 3 that is operational, that is being used for the sweep when it's fully synthesized. So in other words, for a span between less than 5 megahertz and greater than, I believe, 100 kilohertz, the only phase lock loop that's used is phase lock loop 2 of the 1, 2, and 3. M&N is always used. So when you get a phase lock loop 2 or a YIG unlock, and you have phase lock loop 2, that's the most probable scenario because it's used all the time. On very narrow spans, then you'll see perhaps a phase lock loop 3 unlock or 1, and those 2 are rare. They do occur. Most likely you'll see a phase lock loop 2 error. That is not a trivial. The phase lock 2 system is, in my opinion, the most troublesome to troubleshoot in the phase lock loop system that they have here. The M&N just doesn't give problems too much. Phase lock loop 2, the more problematic of all the locked loops. So if you do get a YIG unlock by itself, that's the best scenario because it's most likely has to do with hopefully something relatively simple like C7 being blown on your A20 card,
or perhaps a bad connection on A19 or A20, perhaps the setting of the 6.15 and 2.3 potentiometers, which set up the correct operating point for the YIG. So that's most likely what you're going to find is the issues with a YIG unlock signal. Okay.